start. Last time we talked about chain rule, and this time we're gonna continue on chain rule actually. But this time I'm gonna start off by doing some examples, and yeah, that's how we're gonna start. So the first example I want to do is this example. So we want to determine whether a function like whether say f of t equaling to t squared e to the 5 minus t is increasing or decreasing. Is increasing or decreasing. Okay. So so we have to recall two things here. If f prime of x is greater than 0, we say the function is increasing. Okay? If f prime of x is less than 0, we say the function is decreasing. So to find whether it's increasing or decreasing, we have to first find when f prime of t is 0. First, so let's do this. So taking the derivative of this, right, we have to apply the product rule. Using the product rule, we get 2t e to the 5 minus t, right? And then we get minus t squared, right, e to the 5 minus t. And if we factor this out, well, we can factor this, we can factor this, and we can factor our t out, right? So we get t we get t e to the 5 minus t times 2 minus t equals 0. Okay, so either this is equals to 0 or either this has to equal to 0, right? So what do we get is we get either t equals 0 or t equals 2 is the answer for this. Okay. Okay. So when t equals 0, t equals 2, f prime of t is going to be equal to 0. Now, we have to find whether the function is increasing or decreasing. So between 0 and 2, there's the number 1. So we can test. So let's draw a line. Okay, let's draw a line. And we start from minus 2, minus 1, 0, 1, 2, 3, 4, and etc., right? So we have 0 and 2, so here, let's make this 0 and 2. Right? 0 and 2. So a number between 0 and 2 is 1. Right? It's this number 1. Right? So we can test with this number if whether it's increasing or decreasing between 0 and 2. So if we do that, right, we get f prime of 1, right? Well, f prime of x is equals to this, right? So it's going to be 1 times e to the 5 minus 1 times 2 minus 1, right? So this is going to be e to the 4th, and e to the 4th is clearly greater than 0, right? So f prime of 1 here is e to the 4th, right? So therefore we can say f prime of t is clearly greater than 0. What happens if it is greater than this? So let's plug in. So what happens in this 2 to 4 area? Well, you can see the number between that is 3 here, right? So we can plug in 3 to see what happens. F prime of 3, right, is equals to what? It's going to be 3e to the 3e squared times 2 minus 3, right? What we get is 3e squared minus 3e squared, and this is clearly less than 0. So here we can say f prime of 3, right, is equals to minus 3e squared, and therefore f prime of t is clearly less than 0, right? Now what happens when it's less than 0? And one of the numbers we can test is negative 1. Right? It's a negative 1. So in negative 1, we have what? F prime of negative 1, right, is equals to negative 1 times e to the 6th power, right, times 2 plus 1. So it's going to be negative 3 e to the 6th power, and this is clearly less than 0. So f prime of 1, f prime of minus 1 is equals to negative 3 e to the 6th, e to the 6th, and therefore f prime of t is going to be less than 0 in this case. So we found out for each situation, what happens for each situation, right? This is one of the applications that we can do. But another thing before I say I go to another application, what happens at 0 and 2 if you plug in 0 and 2 to this function, right? Suppose we plug in 0 and 2. F prime of 0 is going to be 0. And f prime of 2 is also going to be 0. So 0 and 2 are called the critical points. They are called the critical points, and you'll see this in a sooner video, but these are called the critical points of the function. Okay, this is important. And let's do another example. Let's see what can I show? And we can do another similar example to this. And this example is determine where v of v equals to v to the fourth power of times 2v minus 8 to the cubed power is increasing or decreasing. Okay, so similarly, we start by taking the derivative. So we say dv dz, right, is equals to 4z cubed times 2z minus 8 cubed plus z to the fourth power times 3 times 2z minus 8 squared times 2, right? And this here, we use the chain rule, right? We use the chain rule right over here. And if you simplify this all up, which I will leave you as an algebra task to do, you're going to find that this is equals to 2z cubed times 2z minus 8 squared times 7z minus 16. Right? So next we have to find when this function here, right, is equals to 0. So setting this equals to 0, if you do the algebra, you can find that this is equals to 0 when z equals to 0, z equals 4, and z equals 16 over 7. Now, I gave you these 3 points. So these will be our critical points. Now, as an exercise, I want to draw a number line and figure out when the function is increasing and when the function is decreasing. I'll leave this problem to do by yourself. Okay, now, that is for now enough of chain rule. And I want to go back to talk about something new. Something we didn't really talk about before. And that is something called the mean value theorem. So, the mean value theorem. Mean value theorem states that if f is continuous, on the closed interval, a and b, right, if it's closed, and differentiable on the open interval, for a and b, right, exists there exists. So this sign here, I'm gonna start using this. This means here is there exists. Just keep this as a reference because I'll be using this quite often. There exists at least one C. C in the open interval such that f prime of C is equals to f of B minus f of A over B minus A. Okay? All right, now let's talk about history a little bit before I go in more detail. Let's think about this function here. Realistically, the equation f of b minus f of a over b minus a describes a secant line. Right? And what do I mean by a secant line? Well, here, let's give it a graph. Right? If you give it a graph, suppose we have a parabola. Right? A secant line is a line that intersects 2 points, literally. So, suppose it intersects it here and here. We can move this point, so by drawing a lot of secant lines, by approximating a lot with approximation of with a lot of secant lines, we can find the tangent line, because the tangent line, if you see, it's going to be something like this. It's going to be this. It's going to be touched at one point, and it's just going to go like this. So, how can we get an equation of the tangent line? So this here, let's name this. This here, right, is the secant line, right? Here, this one is y equals f of x, right? And this is the tangent line. Right? So, how can you go from the equation to secant line to a tangent line? Well, if you see, we previously said that some dy dx, right, is equals to the limit as h tends to 0 of f of x plus h minus f of x all over h, right? Now, what happens if this point came all the way up to here? Went here. What happens if we drew infinite amount of secant line, right? Infinite amount of secant line to get to this point over here and to just intersect at this one point. Well, this happens when the limit as b tends to a, f of b minus f of a over b minus a. Okay? So this here will be another equation of a of a tangent line. So the slope of the tangent line, in conclusion, m slope of the tangent line can be thought of like this. For a function y equals f of x, can be thought as limit as x tends to a, right? F of x minus f of a over b minus a over b minus a. If it is obvious on the closed interval a and b, right? If it is on the closed interval a and b, we can think of this as the tangent line, and it appears so that this is actually the derivative. Or more commonly known as the derivative of the function. Okay? Okay, now I kind of gave you an idea of how this works. So now let's go back to mean value theorem and let's try to understand if f is continuous, right? If f is continuous on the closed interval ab and differentiable, right, on the open interval ab, there exists at least one c in ab such that this is true. So, well, a continuous function. So let's put it this way: a differential function is always continuous, always. It's going to be always continuous. But a continuous function is not necessarily differentiable, or it's not. That's not a must. But a differentiable function is always continuous. Okay, so this is another important thing. Another important thing to know is a differentiable function is always continuous. Okay, it's always continuous, and this is not really an exception. It's always continuous. But a continuous function is not always differentiable, and you'll see later why. But so I think I should stop talking here about like the geometrical aspects of the mean value theorem. Instead, I think I should do an example or two about this. Okay, so let's do an example. All right, let's do an example here. So suppose we're given saying find the number c where c guaranteed by the mean value theorem. For some function g of x is equals to x plus 1 cubed on the interval minus 1 to 1. Okay? So how do we do this? Well, first we have to know that if it meets the conditions. The conditions are, so question, does it satisfy by the conditions? Right, does it satisfy the conditions? Right, and let's see if it does satisfy the condition. The first condition it has to satisfy is this. G of x, right, must be continuous on -1 to 1. And it is. This is true. Okay? The second condition it has to satisfy is g prime of x is g prime of s exists. Better word. G prime of it exists on -1 to 1. On the open interval -1 to 1. Okay? So from here, we know that this here is A, this is B, right? So we have to find what this is. F of B minus F of A over B minus A, okay? And because, look at this. F prime of C equals to this, some number here. So now if this is this, right? F of B is what? Well, to find this, we have to find F of B being 1, F of 1 minus F of minus 1 over 1 plus 1, right? And F of 1 here, F of 1, right, is equals to what? F of 1 is equals to, where is this one? Here. I'm sorry. Let me delete this again. I'm sorry. So it has to satisfy, sorry, I forgot to. This has to be G of B minus G of A over B minus A. Okay? And now this is equals to G of 1 minus G of minus 1 over 1 plus 1. Right? And to find this, we have to find what? We have to find G of 1. Right? It's going to be 2 cubed. And this is going to be 8. Right? G of negative 1 is going to be 0 cubed. And this is going to be 0. So, this, so G of 1 minus G of minus 1 over 2 is going to be 8 over 2, which is going to be equals to 4. Okay? Now, we have to find G prime of x. So we have to find G prime of x. Now, right? If you find G prime of x, right, G prime of x by chain rule is equals to 3 times x plus 1 squared times 1. So because the derivative of the inner function here is 1. So really, if f prime of c, so no, before this, so g prime of c is what? 3 times c plus 1 squared, right? So g prime of c is this. So now f prime of c equals f of b minus f of a over b minus a, right? So now what we have to do is we have to set this equals to each other. So this means that 3 times c plus 1 squared is equals to 8. No, it's equals to 4. Sorry, because the g of b minus g of a, this is 4, right? So doing the algebra, we're gonna get the following. So if you do the algebra here, right? C plus 1 squared is equals 4/3, right? This means the C plus 1 equals 2 over root 3, right? Or plus or minus of this, right? Then therefore C is equals to -1 plus or minus the 2 over root 3, right? Now, so doing a problem with the mean value theorem is not so difficult, but understanding the concept of the mean value theorem is actually pretty important. So I want to go over some basic derivations of the mean value theorem. So here. So we're going to prove the mean value theorem. And we're going to do it in an interesting way. The reason why I'm proving mean value theorem is we're going to apply this, the knowledge of what we learned in mean value theorem, to do two things. First, to find the tangent line, to learn how to find the tangent line. Second, to learn something called the L'Hopital's rule. So to understand the mean value theorem, we have to understand another theorem. That another theorem is called the Rolle's theorem. So you can think of Rolle's theorem as a special case of the mean value theorem. So let f be continuous. On the closed interval, and differentiable on A and B. And let us assume that f of A equals f of B equals 0. Then there exists a point, and let us call this point x0 in A and B, such that which f prime of x0 equals 0. So this is a Rolle, and it's a special case of Rolle's is mean value theorem. So this is assuming that when f of A equals f of B equals 0, right? They're both equal to 0. Then there exists a point, say x0. So this x0 is similar to the C above in the open interval A and B, such that the derivative of f prime of x0 equals to 0, right? So we can prove this. Okay, how do we prove this? So if f of x equals 0 for all x in A and B, right? For all x in A and B, we can choose x naught in A and B, assuming that f is not 0 everywhere. Assuming that f is not 0 everywhere. So if f prime of x naught is 0, we have a critical point, right? So when f prime of x naught equals, so here we have to realize when f prime of x naught equals 0, this means we have a critical point. And if we have a critical point, this means we can have a maximum or a minimum. And suppose we have a maximum. Suppose f has a maximum at x1 and a minimum at x2. Okay? Since f is 0, since f is 0 at the end of the intervals, because I mean if you have an interval of x1 and x2, then it's going to be 0. It's going to be 0 at x1 and it's going to be 0 at x2 because those are the critical points in a technical manner. Then there exists a point. Then at least x1 or x2 lies on A and B. Lies on A and B, where this allows x naught, f prime of x naught, to be equals to 0. Okay? So this is one special case of the mean value theorem, and this is the proof regarding the thing. Now, to prove the mean value theorem, we have to know about the Rolle's theorem, but there's another theorem we have to know, and this is the horse race theorem. Okay? The horse race theorem says, suppose f1 and f2 are continuous on A and B, are continuous and indifferentiable on A and B. Okay? And assume that f of 1 of A is equal to f of 2 of A. Okay? And that this is important. So this is true. And f of 1 of b is equals to f of 2 of b. Okay? Then there exists a point x naught in A and B such that f prime of 1 of x naught is equals to f prime of 2 of x naught. Okay? And we can prove this too. So let's prove this. So let's prove this. So let f of x be the difference of f1 and f2 such that f1 of x equals f of 2 of x when equals 0. Since f1 and f2 are differentiable on A and B, such that and continuous on A and B, and A and B, then by assumption we said this is equals to this and this is also equal to this. This is also equal to this, such that we can get this. So by assumption, we said f of A equaling f of B to 0, such that f prime of x naught is 0 for some x naught in A and B. Thus, therefore, f prime of 1 of x naught is equals to f prime of 2 of x naught, right? And the theorem is proved. Okay, and here this requirement of f of A and f of B equaling to 0 came from the Rolle's theorem. It was derived back over here, right? Came from the Rolle's theorem. And so supply. So now let's assume. So now, given the function, f and the linear function L we can say that the linear function L sub x, right, is equals to some f of A plus x minus A times whatever this is, f of B minus f of A over B minus A, and so on. Such that L of A is equals to f of A A is f of A. L of B is equals to f of B. Okay? And L prime of x is equals to f of b minus f of a over b minus a. So if f prime of x naught is equals to L prime of x naught, which indefinitely is equals to f of b minus f of a over b minus a for some point x naught in AB, right? We get the mean value theorem. So we get the mean value theorem. Which I wrote it above here. Where did I write it? Above here. Okay? So I think this is enough for this lecture. I might provide some problems in the next video, but other than that, if you're just make sure to understand the mean value theorem and the proof of it while understanding some applications to the chain rule. Alright, I hope this video was fruitful and I hope you enjoyed. Thanks, bye.